Morning and welcome. This is our last lecture on the drudgery of differential geometry before we actually get to the main topic of our course, namely symplectic geometry. So the objective today is to tell you about integration on chains and a particularly wonderful theorem called Stokes' theorem, or generalized Stokes' theorem. So if you recall from the last lecture, we introduced simplices. K-simplex, which is the standard K-simplex, which is the convex combination of k plus 1 points in Rk. And we also introduced the notion of the boundary operator. And I'll put operator in quote marks because we don't quite have a linear space on which it acts yet. And what the boundary operator does is it takes a K-simplex and replaces that with the alternating sum of all the k minus 1 simplices that you can build out of the faces of the original simplex. There we go. So boundary operator and standard K simplices. And we did some examples. I'll just draw a picture in this bottom corner here of what's going on. So here's the standard 3 simplex here in R3. 4 points to find this simplex. Remember, the origin is always included in the standard K-simplex. And then if you do D3 on this, then what you get is 1, 2, 3, 4, the alternating sum of 4 simplices, which I don't know if I can draw. Let's see. We get something like this triangle. If we make this the x-axis here, minus, so this is the y-axis here, so we're going to drop that point, so we get this triangle here, plus blah, 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 2 other terms. So that's what the boundary operator does. And now we're going to put it all together to build an integration theory for differential forms on simplices, and then on things called chains, and then eventually we will be able to quote Stokes' theorem. And I'll sketch something resembling a proof of this theorem, but the objective in this course again is not to give proofs, but to give intuitions and examples. You can look up the proof in a friendly mathematics textbook of your choice. All right, now let's get to the integration theory on simplices. So we more or less know how to integrate already on an n-simplex when we have an n-simplex and an n-manifold. We've already defined integration in the case of open sets of manifolds. So we're pretty much there. So just to recall, an n-form omega, which has the name volume element, because it's on Rn. So when we have an n-form on Rn, we call it a volume element. We can write it in the coordinate basis as some function of position wedged with all these coordinate bases forms. So that's where we start. We start by writing a generic volume form as in terms of this coordinate basis there. And you see that it's totally defined in terms of this function a of x. And now we're going to define the integration of this form over an n simplex. So here comes the definition. So if you want to integrate this over the standard n simplex, this form here, what is it equal to? Well, equivalent, it's defined to be, so I'll use the define symbol. It's defined to be just the normal integral over the n simplex. Okay, that was easy. Right, so how hard can this be, right? How hard is it to integrate over simplices? The answer is not very hard. So to get you in the spirit of things, let's do an example. Let's choose n is 2. So we've got a 2 simplex in R2. That means it's a triangle. We're going to integrate over a triangle. And let's choose our 2 form to be just dx wedge dy. So we're just integrating like the number 1 over a triangle. So I hope that's something that does not intimidate you. Here's sigma 2, the standard 2 simplex in R2. Here's x, here's y. And we're integrating, according to this definition, we're going to integrate this form over this 2 simplex here. How hard can it be? Well, you could do it 2 ways, right? You could integrate over the square and divide by 2. Or you could integrate along x and then up to y. And that's what we'll do here. So integrating over the standard 2 simplex is just integrating the number 1 over the triangle. Can you do this? I hope so. You integrate along x, and then you integrate up to x dy. Oh, 1 minus x, sorry. And what do you get? You get a half. So that's right, yeah? The area of a square is 1. 1 times 1 divided by 2 is a half. It's all good. let's have a k-simplex in Rm, not the standard k-simplex, but just a k-simplex. So it's a convex combination of a bunch of points, but not necessarily the ones on the axes with unit length, unit norm. And let F be some map. Oh, sorry. This is Rn here. Let F be some map from Rn to this some manifold that you like. And, well, here I say it only needs to be defined on an open set U containing our simplex. And we have the image of this map. We're going to give it a name. Let's call it SK. And this is called, we're going to give this special image of the k-simplex here a name. We're going to call it the singular k-simplex in M. Or a singular k-simplex in M. I'll draw a picture. So you have a simplex, so there's a there's a two simplex there inside R3. Here's U containing it. Here's our friendly manifold. And then you have some function f going from this open set U to M, and then this triangle gets mapped to some kind of curvy triangle in our manifold. And that's our SK right there. It's a singular k-simplex in M. Now, why singular? So what's singular about it? Well, there's two reasons we're going to call it singular. Number one, these SKs don't need to triangulate the manifold. So they don't need to be complete in some sense and cover all of the manifold in little triangles. We just like have anything. And more seriously, there's no notion of independence. Of points. Yeah, doesn't really quite fit. So they're called singular because they don't need to triangulate M. And secondly, and more importantly, there's no notion of the independence of a set of points in a manifold. So in Rn, let's take a look at Rn here. You can talk about points being independent. And the reason you can talk about points being independent is Rn's a linear space. So you can say that the unit vector on the x-axis, the unit vector on the y-axis, the unit vector on the z-axis, they're independent. You can express any point in terms of a linear combination of these. But on a manifold, you've lost that. You no longer have that a manifold is a linear space. You have that as locally a linear space, like really locally on the tangent space, but even approximately near a point, it's no longer a linear space. And so the notion of point independence of points is lost. So that's why we signal that by just adding this adjective here, singular. Now we get to the hard definition. Let's consider the set of all k simplices in M. So it's an uncountably big set, right? Of all singular So this alpha here, J in alpha, I'm just using this to denote the set of all k simplices. Alpha is some indexing set, it's uncountably large. You have to worry about all the coordinates of all the possible images of all the points of this simplex. So it's a very big set. then we're going to take this very big set and take linear combinations of things from this very big set. All right. So very improperly speaking, we think of these as like basis vectors, and we build a vector space from this uncountably large set here. More properly, we build a free abelian group from these things with coefficients in R. But at the physicist level, you can think of these things as being just like basis vectors, and you're allowed to take linear combinations of them. And a K-chain is such a formal sum of these things with coefficients in R. So elements look like, well, let's see. So here's an example of a K-chain. I've written R, but I mean K. So to specify a K-chain, you need a list of numbers, and you need some a singular K simplices, and then a K-chain is just this linear combination. You write it on the paper like that. Don't interpret it anymore. You're not actually adding the points inside the simplex here with each other. You're just putting coefficients in front of a list. The set over here, this set of all formal sums of these singular K simplices forms a group, meaning you can add two such elements and get another one. It's kind of obvious, right? If I have one chain and another chain, what's their sum? Well, it's when you sum up the coefficients in front of these SKs. You can take the difference, and there's an identity element, which is namely 0. It's a K chain where the coefficients are all 0. So it's a free abelian group on these things. I'm going to give it a name. It's called the chain group, CK of M. Now this is the space that we're going to work in. Now I kept talking of D as like an operator, this boundary operator. Now we have a space for it to act on. It's going to act on K chains. It's going to take one chain. We're going to then have it act on the simplices in there. That'll map them to linear combinations of simplices of lower dimension. And then that will be another sum of simplices, and that'll naturally live in the chain group of one lower K. So that we can actually talk about this boundary operator as really as a map rather than just some formal thing. Okay, so if you have we have to connect the boundary operator to singular K simplices. So if you have some map from a K simplex to a manifold, then it's kind of obvious, right? But it's important to spell it out that the boundary of sigma K gets mapped to boundaries in M, or to subsets in M. And why are we saying that? Because we want to act the boundary operator on singular K simplices, not on their original counterparts in the real numbers. And it's important if we're going to really think of this D as an operator or a linear map on this space over here. Yes.
In these chains, do we allow finite, countable, or uncountable sums?
Let me look ahead to see how I did it.
Okay.
I think we only allow finite. For now, let's say finite.
Okay.
Yep.
Sorry, I think you mean instead of SK, the second SK, you mean sigma K.
I do, thank you very much. So instead of SK, I meant sigma K. Thank you. And in answer to the first question, what kinds of sums are we going to allow here? We could have that an uncountably large number of these coefficients were non-zero, or a finite number, or a countably large number of coefficients here are non-zero. Let's stick with finite for the moment until I say otherwise. Only, I'll say it here, at most finite aj not equal to 0. I think that's the safest way to proceed at this point. I mean, in the end, we'll actually focus on a finite number of singular K simplices anyway when we actually do our integration. results. Okay, so this is a very important but trivial statement, because what it allows us is it allows us to extend or even define the notion of a boundary map on the set of k-chains. So it tells us that delta k is a well-defined map on these chain groups. And we have a nice little exercise, a really good one. Take the boundary of a boundary. What do you get? You get 0. So this is one of these. This is the counterpart of this other trivial result about the exterior derivative, that if you do the big D, the little d followed by the little d, you get 0. So what a striking result. It's like straightforward double sum. Just apply the definition twice and you see that there's a cancellation in a double sum. So there's nothing to it, but it's supremely profound. These two observations about delta and d's have really profound consequences when you want to understand whether two manifolds are the same, for example. And I think we're just about done with our integration theory. Then we can get on to Stokes' theorem. Yep.
I don't quite understand why we use the letter C now. But,
The letter C.
sorry, I see it.
Okay.
Yeah, thanks.
Fine. Good, good. Here it is, definition. How do we integrate something on one of these k-chains, which is like a submanifold, like. So let omega be a k-form, and sk a singular k-simplex. then we're going to define the integral of our k-form over sk, just like we do for the standard integral of forms over subsets, but now we have to worry that we have a lower dimensional subset of M, so we have to use pullback maps to do this definition. So integral sk omega is defined to be the normal integral in Rk of the pullback of the map which presents our singular k-simplex to us. I'll draw the picture. So here's a singular, here's a standard 2 simplex. We have a subset of R3. We have some map F. We have our manifold, our 3-dimensional manifold here. If you like, you can sort of imagine that as a 3-dimensional manifold. We have this, the triangle there gets mapped to, I should have a different color access. No other colors here. I see a red. So somehow embedded in R3 is embedded in M is this 2-dimensional triangle, and we have a 2 form on M, and the integral of omega over sk is just defined to be pull back this 2 form onto a 2 form here on this triangle, and then just use your standard integral there. That's the example to have in mind with this definition there.
Excuse me?
Yeah?
This sigma bar, was this the standard?
Standard k-simplex.
And
Oh, all right. Yeah, because I didn't, yeah. Now it's just a k-simplex.
okay, then it doesn't depend on different f because we have translation invariance.
That's right, yeah. It doesn't depend on different f because we have translation invariance. Yeah, okay. And the last thing we want to do is, like, this is just for a singular k-simplex. What if you've got a collection of them sort of joined together, forming a complex? Probably won't talk about simplicial complexes in this course, but if you imagine you've sort of got a collection of triangles in M that are sort of neighboring, stuck to each other, you might wonder what on earth is the integral of such a thing, of a collection of, integral of a 2 form, say, over a collection of triangles, singular 2 triangles. How would we define it? Well, everything's linear, so, and finite. Yeah, so it was important that we had a finite number of coefficients being non-zero in the previous definition of k-chains, because for a general k-chain, C equals some finite linear combination of singular k-simplices we define once more the integral over this chain to be, well, just the combination of the integrals. So easy peasy. And this is all making sense because it's a finite linear combination here. If this was not a finite linear combination, we'd be in for some trouble, especially if it was an uncountably infinite linear combination. Then we're really in for some trouble. Because you can't be sure if that sum converges. And that's it. That's all we need for a large portion of this course. More or less concludes our geometrical background. We'll probably take a break in the later lectures and talk about Lie derivatives and vector fields, flows. We will get to that. But in the next lecture, we'll launch into symplectic geometry proper. But before that, today, I want to discuss this really fantastic theorem called Stokes' theorem. So you've all heard of Stokes' theorem in vector calculus. Well, the Stokes' theorem I'm going to show you today isn't your grandfather's Stokes' theorem. It's a massive generalization. Check I've covered everything. Yep. Here we go. So I don't know about you, but I spent 6 months of my life learning integral theorems in vector calculus. Gauss laws and all that kind of thing in Maxwell, in electrodynamics. And they looked kind of similar, each of these theorems, Green's theorem and so on, but there was no discernible pattern to them. And indeed, historically, these theorems were sort of discovered piecemeal, and it was only later that people realized that they were all instances of a more general and actually arguably simpler statement. Let's see, I'm going to launch into it here. Yeah, here you go, this is pretty easy. So, let omega be a k minus 1 form on an n manifold M, and C some k chain on our manifold M, then C of d omega, the integral of d omega over C is equal to the integral over the boundary of omega. Like, whoa. How easy is that to remember? That's super duper easy to remember, right? Because you just have to remember, I've got like, C is like a submanifold, right? You know, I've got like some space and I integrate d omega, but that's the same as taking the boundary of that space and integrating omega over that. I claim that's pretty easy to remember. The surface area of that result is small. Now try and tell me, quote from memory, the three, the divergence theorems and all those theorems. Can you do it? Like, if I pushed you right now, would you might get a minus sign wrong maybe, or it's possible, right, that you might not remember all those integral theorems quite correctly. But here, this thing there contains all of them as special cases. And I claim that that's easy to remember, or easier to remember. Now, we're going to explore this theorem in the exercises due next week on Friday. And there you'll look at, I think, a slightly different formulation to what I'm doing today. The Stokes' theorem has been generalized to extraordinarily many settings. Here we're doing it in the context of chains, but in the exercises you'll do it in the context of manifolds with boundary, which we have not done so far in this course, but you'll be able to work it out. In fact, manifolds with smooth boundary is where we'll look at the Stokes theorem. However, Stokes theorem has been generalized way beyond that, and so there's this whole body of maths called geometric measure theory, where people look at rough sets, like manifolds with like really rough boundaries, and they see, does Stokes theorem still work? And the answer is, well, yes, quite often. Right? So it's an amazingly general theorem, and in some sense you can see it as a kind of super duper version of the fundamental theorem of calculus, and you will check that out in the exercises. So there's a lot to like about this theorem, and we will use these features throughout the course, and you will get to explore it in the exercises. Okay. I'm not going to prove it, no way, but I'm going to sketch the proof. In fact, I'll just show you like the salient features, and then you'll see as we go through this sketch how to generalize it. Like these generalizations will be simple exercises versus like grand insights. And what I really particularly like about Stokes' theorem is it's a good example of when you get the definitions right, that the theorems are trivial. So this is really this is a feature of really good science, that when you get the definitions right, the theorems should be easy to prove. They should be almost immediate. And if your theorems are really hard to prove, if you're really struggling and need great insights, then probably you haven't quite got your definitions right, or you've chosen definitions that don't mesh well with each other. So it's a general feature that you're on the right track in research when the theorems start getting easy to prove. And Stokes' theorem is easy to prove. You'll see, as I go through this proof sketch, how the proof amounts to evaluate left side, evaluate right side. Are they the same? Yes, done. That's how the proof actually goes. Well, we'll tackle both sides. Let's tackle the left-hand side first. All right, to do the left-hand side, we're going to need a little lemma, which is an exercise. Actually, we got some time, so maybe I even sketch how to prove it. I think I made this as an exercise earlier in the course. Well, now you get to see the answer. Okay. So firstly, we've got a chain here, right? That's a linear combination of singular case simplices. But like the left-hand side is a linear combination, and the right-hand side will be the same, basically the same linear combination. So let's just fix our attention on one simplex. Just prove it for a singular K simplex SK. So I'm not going to prove it for chains. That's your job. But then like it's not going to be a big chore because it's just a linear combination. Okay. Well, this is a singular K simplex, so it's the image of some simplex, right? And in particular, you can, by judicious choice of F, choose our, you can always choose by translations, rotations, dilations, and so on, that this singular K simplex is the image of the standard K simplex under some map F. There's enough freedom there to do that. So to get started on this left-hand side, we just insert now into the left-hand side the definition of the left-hand side. Let's do it. S, K, D, omega. It's the left-hand side of Stokes' theorem applied to a single singular K-simplex. What do we do with that? Well, by definition, that's equal to this. Right? I just use the definition, nothing more. And then the next line is the exercise, which I will actually, because we have time, I'll go through and show you roughly how that works. The exercise is that is this. It's probably the trickiest bit of it. F star of d omega is the same as d of f star omega. It's like, is this obvious? Well, to some people this is obvious, but you know, it needs a bit of a computation. Let's see if we can prove the exercise there. F star on omega. Omega is a k-1 form. I'm going to write this out in coordinates. We'll do it that way. Okay, so that's what the pullback of a k-1 form looks like in coordinates. You just hit it with the inverse Jacobian everywhere. So this should be familiar to you from general relativity, this kind of coordinate expression. And then, in order to prove the exercise, we want to show that f star of d omega is equal to d of f star omega. So I'm going to hit this with a d. D of this. We'll see what happens. So then you get an additional sum over m, sum over the l's, sum over the j's, omega, coefficients, all this stuff. And then you get an additional dxm wedge with all that. And I've got to take the partial derivative with respect to xm of omega. So that's how you do an exterior derivative on something. And then that's already the right-hand side of the exercise. And the left-hand side of the exercise is to do it in reverse. We'll see what happens. So d omega you've got to take the d of this. But now we're in the coordinates patch on the manifold. So it's the sum over the j's of omega j's d ym in this case. And you wedge on the y. And now we've got to take the f star of this. We've got to pull it back. And that just gives us a inverse Jacobian term for each of these things. And then we're really done. Because, look at that. And then if you just compare this expression here with that one there, then we're done. Probably a more elegant way to prove that, but I like doing things in terms of coordinates, because if you actually ever want to do a real calculation, you'll end up doing it in coordinates. If you want to get a number that's not 0 or infinity or 1, then usually you'll have to get your hands dirty with a coordinate system. Or maybe integers. Maybe you can do it without, get answers which are integers without getting too dirty, but yeah. All right, so this is just some, like, you know, there's the proof of this exercise. Here's the simple exercise. We proved that. Wasn't a chore. Now, let's look at the, that was the right-hand, sorry, the left-hand side of Stokes' theorem. Yeah, and now I think we're going to look at the right-hand side, indeed. What about the integral over the boundary of a k form? K minus 1 form? Well, the definition, right, of that integral is just the pullback integrated over the boundary. That's just the definition there. So our task now is to show that that equals that. All right, let's get to it. So I'm going to write the task in a slightly more general way. Yeah. We're going to prove something slightly more general than this task. There it is. That's what we're going to do. Okay. So our job, if we could show this, right, then we'll have shown this, because that's a K form, and that's a K minus 1 form, and, well, those are the standard K simplices. And so we just substitute psi equals f star omega, and then we're done. Oh. Let's do it. Oops. So let's commence with the, what are we going to do? I think we're going to do the left-hand side first. What does the most general k minus 1 form look like on r to the k? Yeah, it's a linear combination, basis forms, a, mu, depends on coordinates. That's what the most general k form looks like. The k minus 1 form looks like on r to the k. Don't get much more general than that. This is the basis, coordinate basis. The space of k minus 1 forms is k-dimensional and is spanned by wedging all of the coordinates except for 1. And that's what's happening here. We're missing out the muth coordinate 1 form. So that's the most general possible k minus 1 form. Now, here we're not going to do the complete proof. Instead of doing the most general one, I'm going to look at an example one, and then you'll work out how via linear combinations to generalize this. So we're going to look at an example k minus 1 form, which has a slightly more special form. Namely, it's not a linear combination of k of such things. It's only one of these basis k minus 1 forms. That one. We can look at this one. So if you want to generalize this argument to the most general k minus 1 form, then you just have to see what happens on all forms of this particular structure, and then take linear combinations afterwards. But I claim that the kernel of the proof is already can be found in this example there. Let's do the d of it. What's the exterior derivative of psi? Well, it's this, right? The definition of the exterior derivative. And depending on k, this could be plus or minus the following thing. So if k minus 1 is even, then you can use the anti-symmetry of this wedge product to move it past an even number of times, and you pick up a plus 1. And if it's odd, then you pick up a minus 1. And then let's just put this into the left-hand side of what we want to show. See what happens. So this is well, okay, I've skipped a step or two, so there is some exercise work here. So if you insert exactly this k form into the left-hand side and use the definition of that integral as just a normal k minus 1-fold integral, then what you end up having to integrate is this expression here, x1 to xk minus 1. And in the kth argument of a, remember a depends on all k coordinates, that's actually determined because we're on a simplex by the sum of 1 minus the sum of the other coordinates. So you need to think that through a little bit. Why is this actually true? Minus, minus, minus 0. So I'm not going to give everything to you. You have to work for that little bit. So I hope intuitively it's kind of clear what I did there. You know, we have the integral of the derivative of something. Integrals get rid of derivatives, and we're good, right? Right-hand side, let's hit it. So that, the hard work on the right-hand side is working at the boundary of this standard k-simplex. Now that's equal to these convex combinations. As before. Minus 1 to the k, p naught, p1 to the p, k minus 1. So we've got k terms there in this boundary, I think. No, wait, k minus 1, right? Hang on. K minus 1 terms are in that boundary, yep. But, and here's the best bit, right? If you integrate, this is a chain, right? This is a k chain, a k minus 1 chain, k minus 1 chain. So the integral of anything over a k minus 1 chain is just the sum of the integrals over the constituent simplices like this. That's just vector calculus, not even on manifolds or anything. This is just in real space. But almost all of these integrals, I mean a lot, are actually just plain 0. There's just lots of vanishing terms here. For example, and this is a consequence of the fact that the 0th coordinate is equal to 0 on, say, this simplex here. Lots of zeros. And that means that, in fact, when you work it out, when you actually work out this integral here, you find that all but 2 terms are 0. namely these two. And your last little exercise is to show that that equals the left-hand side. Which you can probably do by just looking at the left-hand side over there. I have a feeling that I made a mistake here. No, 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 it's all good. I made a mistake there. Yeah, x1. Right. So that's the proof of Stokes' theorem. I think we're done with it. There are lots of little missing steps in here that you have to fill in. I did it only for this one example, k-1 form up here. But a most general k-1 form is a linear combination of k of these things. And then you have to, for each of those things in that linear combination, you have to run an argument similar to this one. But you can always argue that there's a permutation that brings every term into this form. And then you have to worry about linear combinations and checking them on both the left-hand side and the right-hand side. But otherwise, that's how the proof goes. So we're basically done now for differential geometry for a while. I'll mention one interesting, obvious consequence of Stokes' theorem. That's Stokes' theorem. Integral over a manifold of d omega is the same as the integral over the boundary of just omega. So what if d omega is 0? So that means that omega is closed as a differential form. What does that tell us? That tells us something rather interesting. Pretty cool. That's something that you have to argue quite hard for in vector calculus. You have a divergence-free vector field. What's the integral over a volume of a divergence-free vector field? Poof, 0, right? There it is. This is like a complete supergeneralization to all dimensions of that. Neato. All right, I think that's it. I'm going to stop here because we won't really have time to start symplectic geometry proper. And tomorrow we will get onto symplectic, the best form of symplectic geometry, namely symplectic linear algebra. That's the kind of case always, right, in geometry. What you're trying to do is take all the lovely, beautiful things that you know for Rn and take as many of them over to this more general setting as possible. Now, you lose things like the ability to form points with linear combinations, but you preserve other aspects. So symplectic geometry is no different, right? We take the most beautiful example of a symplectic manifold, namely a symplectic vector space, work out all its beautiful properties, and then try and transport as many of them as possible over to these more general objects called symplectic manifolds. And that's the objective of the next chunk of this course, with a good couple of examples in physics. And yeah, we'll commence that in the next lecture. But for now, thank you very much.